In this video, I'm going to provide an overview of PEDCO's Adsorptive Gas-Dryer Simulation software. After the software is installed, it can be launched as with other Windows applications. The software can be used to simulate the performance of thermal swing dryers, including open loop blower, closed loop blower, heated process gas or heated compression dryers, as well as pressure swing dryers, including a conventional pressure swing where the purge is exhausted at atmospheric pressure, a vacuum purge dryer, a single tower dryer where you would have intermittent use of the compressed air, and lastly, it can simulate the performance of once-through dryers, which are non-regenerative type dryers. Note that the program can be run in English units or SI units. For the purposes of this demonstration, I'm going to run the simulation in English units, and I'm going to select the once-through dryer type. The reason for the once-through dryer type is it's the simplest dryer type, and consequently it makes it easiest to explain the capabilities of the simulation program. So once we've selected the dryer type, the units that we want to operate in, we click on the select button. The program will take us to a flow diagram for the specific dryer type to be simulated, in this case the once-through. Now the flow diagram for this is very simple. You just have a desiccant vessel, inlet in one end, outlet in the other. What I'm going to start to talk about a little bit is the default values. This program was designed to make it as easy as possible for someone to run, but also to provide the flexibility that the dryer engineer may require to be able to try different what-if scenarios. But you'll find in all the sheets there's a default value that you can click, and when you click that, it'll populate all the data fields with some reasonable set of and consistent set of data. Let's just start on the left-hand side here. In the desiccant vessel, you see a button where we can select the desiccant. If we click on select desiccant, it takes us to a form where you can input the information with regard to the desiccant material. You'll note that you have the capability to layer your desiccant with up to 4 layers. If we click on this drop down, you'll notice that we can have mixtures of desiccant actually. Activated alumina, silica gel are options. Molecular sieve 3A, 4A, and 13X are options. Spherical silica gel, the standard grade, and the water-resistant grade are options, as well as you can have user-specified desiccant material where the program would read desiccant physical property data from an Excel file that the user would create. For the purposes of this simulation, I'm going to select activated alumina, and once I click on any one of these data fields, you'll note that all the rest of the data fields are populated with default values. And for the purposes of this overview presentation, I'm not going to talk about all the data that's required. One thing I will note is that you have the ability to layer, as I mentioned, and I'm going to just specify that 50% of the desiccant's activated alumina, and I'm going to specify that 50% is molecular sieve, and you'll see that it was smart enough to know that if you've already used 50% activated alumina, that this should be 50%. Moving on, I have a valid set of desiccant data, I'm going to click on OK, and it takes us back to the flow diagram form. There's a set of data here for the vessel information. We have to specify the OD and the ID of the vessel, the length of the vessel, which tells us the size of the desiccant bed, the R value for heat transfer from the vessel to the ambient, and the value of 0.5 is a good natural convection coefficient for if an uninsulated vessel. If there's insulation added, then this R value would be increased. The specific heat of the desiccant, or excuse me, the specific heat of the vessel material is necessary, as well as the density. And I'll pause here to note that when you hover over one of these data cells, you'll see a tooltip that gives you a little bit longer description of what the input data is, in this case, density of the vessel material. Continuing, ambient conditions must be provided, the temperature and the pressure. Initial bed conditions have to be provided, and this basically tells you how dry the desiccant is initially. In this case, I'm saying that with a desiccant at 100 degrees Fahrenheit, it's capable of producing minus 40 degree dew point in the gas stream. Also, operating conditions are necessary. Flow direction, which is not very significant for a once-through dryer, so I'll not talk about it. But gas type, the time of the simulation, the flow rate, the temperature, pressure, and dew point. And I will note also the gas type, you have the option to select a number of different gases, including air, argon, carbon dioxide, ethane, helium, hydrogen, methane, nitrogen, and oxygen, as well as a mixture of any 4 of the above gases. For this simulation, I'm just going to run air. Moving over to the right-hand side here, we have a number of buttons that we've also already used the default values button. There's a group of them here: output control, numerical systems, and transport coefficients that take you to additional forms where you input more data. I'm going to click on the output controls, and you'll see we go to a window that's with output control data, and we click on the default values, and again it populates. And I'll point out that the output control, when it populates the defaults, it's not always the same values. It looks to see what dryer has been selected, what the runtime is. It looks at the numerical system to see how many grids are specified for the bed. So it uses some intelligence before it just selects randomly what the output controls would be. I'm going to use the default values here just in the interest of time, and click on OK. So now at this point I'm going to take a shot at running this program. So I'm going to click on the Run button, and what it comes up with is a warning that says no numerical system data was specified. You want to use the default values. Well, you may recall we didn't go into this numerical systems form here. What I'm going to do here is I'm going to show you how, when this warning comes up, do we want to use the default values? I'm going to say no. And when we click on no, it takes us to the numerical systems form. I will click on the default values here, at least to get me a starting point. And I'm just going to say, all right, instead of using a 1 minute time step, I'm going to use a 2-minute time step. That will make the program run a little bit faster. The accuracy of the results will be diminished slightly, but not significantly. I'll click on OK, and we'll try the run one more time. We click on Run. Now it's saying another warning: no transport coefficient data was specified. You want to use the default values. In this case, I'm just going to say yes, let's use the default values. And then we get another warning, and this sometimes gets to be a little time consuming with these warnings, but what we're trying to do is make sure that we have a complete set of valid data before we run the simulation and just get junk results because the input data wasn't correct. What this is telling us is the gas velocity may create movement in the desiccant if the gas flow is upward. The pressure gradient of 30.5 pounds per cubic foot is greater than 70% of the bulk desiccant density. Do you want to increase the vessel diameter? So if we increase the vessel diameter, the velocity would drop, and then the pressure drop gradient would be reduced, and we wouldn't be in danger of fluidizing the desiccant. And I'm going to pause here and indicate that the simulation program has a number of air trapping levels. It'll look at each individual piece of data that's entered, and it may tell you that, hey, it's physically impossible, or that it's unusually high or low, and give you an opportunity to change it. It'll look at relative relationships, for example, between the OD and the ID of the vessel, and clearly you can't have an OD that's smaller than an ID, and if you try to accidentally enter those types of values, the program will stop you until you make a change. This warning here, this is requires the diameter of the desiccant bed, the gas velocity, the pressure, the temperature, the desiccant type, and all that information is required before it can make this an assessment. And consequently, it doesn't do that check until you actually try to run the program. And do you want to increase the vessel diameter? We're going to say no. And what we'll see is that the program will launch Excel. When the program launches Excel, one of the first things it does is it creates a model number type Excel file name, as you see here, and I won't describe what all the numbers and letters mean, but suffice it to say that it tells you an awful lot about the specific dryer that's being simulated at this point. It has to save this file in a folder, a temporary folder that the program created, and if you've run these same conditions previously, it's saying, hey, that this a file with this name already exists. Do you want to replace it? And I'm going to say yes. And then at that point, everything is happy, and the Excel workbook is set up. You see, and there were a number of sheets that were created. I'll go through these sheets very quickly one at a time, but the input sheet, this includes all the input data that was provided on all the input forms. There's also an input form in SI units for those folks that are more comfortable with SI units. There's a form or a sheet that has the desiccant property data, so if you want to go and see what this equilibrium loadings for the desiccants that are being used, what the program is using, you can go into this sheet, and you can see what the bulk density that's used and the voidage and heats of absorption. That information is all saved here. You can look at the thermophysical properties of the gas, things like viscosity, thermal conductivity, specific heat, and whatnot. There's a sheet that shows the dependent variables being dew point, loading, and temperature. Versus time, so the time on the column on the left. This information, the dew point, the loading, and the temperature is available at 4 positions in the bed: the drying, a quarter of the way through, halfway through, 3/4 of the way through, and on the drying outlet. And this is the data that's plotted on this plot sheet, and the program is completed. So, but let's just go back. There's a detailed output sheet that gives you a snapshot of the conditions in the bed at a particular point in time. In this case, it's 30 minutes after the simulation began, 60 minutes after the simulation began, and you can see through the bed what the bed temperature profile looks like, what the loading profile looks like. The plots will come back to that. Heat and material balance, what you're looking for is to verify that the heat material is balanced, and that will always be the case. Temperature and concentration distribution. This shows you what the temperature through the bed, in the vessel, and what the gas concentrations are, both in the gas and in the pores of the desiccant bead. And this would be used in the event that you want to restart a run that was previously completed. And then finally, temperature and concentration distribution in SI units. We'll go back to the plot sheet, which tends to be one of the more useful sheets in this workbook, and we can see we have dew point, loading, and temperature as a function of time. You may recall seeing on the dryer flow diagram sheet that we were simulating for 2 hours. There's 5 different lines on each one of these graphs. They go from the drying inlet end, the black diamonds, to the magenta squares, to the red triangles, to the blue crosses, to the green asterisks. And to explain this, let's take a look at the dew point. So the green asterisks are the drying outlet end, and if we look initially, it started at -40, and we did specify that the desiccant was capable of getting us some -40 dew point at 100 degree temperature. And what you see very quickly, the dew point climbs, and if we click on this and hover, you see a dew point of -28 degrees Fahrenheit. So the dew point's climbed from the -40 where it started. And the reason it climbed is if you look at the temperature down here, our inlet temperature was 100 degrees, initial bed temperature was 100 degrees, but your heat of absorption is going to cause the gas temperature to increase, and consequently the bed temperature. And as we all know, desiccants don't work as well at high temperatures, so instead of creating a -40 or producing a -40 dew point, you're producing a dew point that's closer to the -30. And once it climbed to -30, because the temperature increased, it stayed relatively constant for the 2-hour duration. But if we take a look at the 3/4 point through the bed, here at 3/4 point, at roughly an hour to 1.1 hours, the dew point there starts to break through. So what you can see is that you probably have a bed that's sized reasonably well for the temperature and pressure and flow rate that was specified, because you got breakthrough 3/4 of the way through, but you didn't get breakthrough at the outlet end, which is what the end user is concerned about. But as a dryer engineer, you want to be able to see a little more about what's going on down inside the desiccant bed, so you can assess whether the dryer's way oversized or whether it's just size, so the performance is just on the edge. So with that, this gives you a very quick overview of the capabilities of PEDCO's Adsorptive Gas Dryer Simulation software. And I thank you for your time, and